While design patterns and principles are meant to help you, the general idea of them is to allow a project to get bigger without becoming an unmanageable mess. After all, if your game is small enough, you can pretty much write it any way you want and it will probably be fine. In contrast, trying to rigidly follow design principles because they are the right way to do things, without fully understanding why, can easily cause you to over-engineer your project. At both ends of the scale, the worst case result is likely to be that you won't finish your project. Without structure, your game can quickly become complicated and you won't know how to progress it beyond a certain point, while following design rules too rigidly can prevent you from getting anything done, as you overconsider the hypothetical results of all of your actions. So what's the answer? How can you balance flexibility and structure? While there isn't a one-size-fits-all solution, a general approach is to understand the intentions behind the various rules so that you can break them with confidence. That way, when you choose to do something in the wrong way, because it's easier, you know exactly what risk you're taking and whether or not it's likely to cause you an issue. We're going to look at one of the most popular sets of design principles for writing maintainable code, Solid. This set of 5 general rules seems simple enough at first, but actually applying them as a beginner in Unity can be surprisingly difficult. So what are the 5 solid principles? How can they be used in Unity? And when should you be following them?
This video is sponsored by Skillshare. Skillshare is the largest online learning community for creatives, with thousands of classes led by industry experts in design, development, and content creation, making learning a new skill easy. For example, I wanted to improve the production quality of my videos, so I use Skillshare to learn how to use Fusion, the motion graphics software that's built into DaVinci Resolve. I've also been exploring some of Skillshare's game development categories, such as 3D modeling, pixel art, and shaders. And if you're interested in trying a class for yourself, the first 500 people to use my link in the description will receive a 1-month free trial of Skillshare. Get started today.
The first of the 5 principles, the single responsibility principle, is probably one of the easier rules to apply to your own scripts. But even though its definition can be relatively straightforward, it's still easy to take this principle too far. The idea behind single responsibility is that a script should only have one reason to change. However, it's easy to assume that single responsibility means that each script only does one thing, which, if you take this advice too literally, can be very difficult to implement. After all, one thing can be very specific. Instead, the general idea, and the since clarified description of the single responsibility principle, is to keep the code that changes for the same reason together. For example, a movement script might move the player and make them jump. That is clearly 2 things, meaning that if you took single responsibility to mean one task, you'd need to create 2 different scripts. 3 when you realise that both of these systems require a ground check to work. In reality, trying to split these systems out can be more difficult than keeping them together. For example, they all use the same data, they may reference the same external components, such as a rigid body, and generally all do one thing, move the player. So is it okay to put them together? Ultimately, the definition of a responsibility is up to you, meaning that you will need to decide if any one part of this now combined system will need to be changed separately to the rest. For example, let's say that your movement system combines jumping, moving left and right, and a ground check. Would a non-controllable object in your game ever need to check whether or not it's grounded? If you have movable objects in your game that cannot be controlled, you might need to check whether or not they're touching the floor. In which case, you may choose to split out the ground check into a different component to avoid rewriting it. But now you have to find a way for the movement and ground check scripts to communicate with each other. In this example, if it's unlikely that you're going to create any kind of movable object that doesn't require a ground check, but you may need to create a groundable object that can't be controlled, then it's possible to split out the scripts without reducing their cohesion by using inheritance. For example, a groundable base class can be used to provide ground check functionality to both derived scripts, while the logic that allows an object to be controlled only appears in one. This works because this specific hierarchical relationship allows it to. an object is likely to only have one version of the script or the other, not both, meaning that the ground check won't be fired twice, and implementing it as a base class allows the movement script to use it directly, as if it was one of its own members, satisfying single responsibility, but without reducing cohesion. While this won't always be possible, it can help to remember that the idea of single responsibility is to make your life easier, not harder. Separating every class into different small parts just for the sake of adhering to a general rule may be helpful in some cases and unhelpful in others. After all, single responsibility is a two-way street, meaning that it's just as important to keep classes that do change together, while separating the code that may need to be changed or accessed independently in an appropriate way that's as convenient as possible. The open-closed principle stands for keeping a class open for extension but closed for modification. Generally speaking, this means allowing a class to be extended or added to, but without being fundamentally changed. You might assume that this is something that will only be relevant later on in your game's development, when certain classes that already exist have well-defined roles, meaning that they're relied on by other classes to work in a certain way and are essentially finished. However, while that is a relevant consideration, that only focuses on the closed part of the principle, not the open. Open for extension means that you can add functionality to the script, but there are two interpretations as to what that actually means. Meyer's open-closed principle, introduced by Bertrand Meyer in his 1988 book Object-Oriented Software Construction, suggests the use of inheritance to extend the functionality of a class without affecting the original, or any other scripts that might rely on it. However, the principle has since been redefined into a more general polymorphic open-closed principle, where abstraction through an interface allows you to make a class modular through the use of a generalized output. But what does that actually look like in Unity? A closed script is well defined, meaning that it has a core purpose and offers limited public accessibility, typically through public functions. At this point, changing the script means changing how it works, which, while you may need to do that, has wider reaching implications, especially if the script is already being used in your project. As a result, you should only need to go into the class if you actually want to change what the class does or how it does it, not if you want to extend it, meaning do more of what it already does. For example, let's say that you have a script that detects a collision with collectible objects. To detect a pickup, you might try to get a specific pickup script, such as a points pickup. Technically, this is not open for extension, since if you plan to have the player pick up a different type of collectible that uses a different script, you will need to go back into the collector class to check for both types. While this example is simple and relatively harmless, creating a situation in which you have to change a class just to allow it to do more of what it already does can cause issues. In this case, because the class isn't open to extension, because you have to manually change it to extend it, it also can't be considered closed. The solution is to generalize the class's output, in this case by using an iCollectible interface, which would allow you to add new pickups that implement the same interface, or through inheritance, which would allow the collector to pick up different objects using subtyping. In Unity, there are many different ways to generalize the output of a class, such as with interfaces, inheritance, Unity events, and delegates, but in all cases, the general idea is the same, that you should only need to change a system if you actually need to change the system, and simply extending it to do more of what it does shouldn't affect how it works. The Liskov Substitution principle is a guideline for using inheritance correctly, and it requires that you must be able to use a derived class in place of the class that it inherits from. If you're already using inheritance in an appropriate way, that is, if the relationship between a subtype and the class it inherits from is already hierarchical, then you're probably already adhering to this principle and you don't need to worry. However, it's possible to use inheritance in a way that seems like it should work, but actually doesn't, in which case the Liskov substitution principle is a good test to check to see if your hierarchy is appropriate. In simple terms, when you create a subtype, you should be able to pass it in place of the type it derives from. An example of this is the various individual collider classes which can be used in place of their hierarchical parent, the collider. Any of the specific collider types can be passed in and used as if they are a type of collider. The only functionality that may be missing is any additional logic that only exists inside of a specific collider type. This adheres to the substitution principle. So what does a violation of the principle look like, and why is it a problem? A violation of the principle is realistically going to be a relationship that seems hierarchical but isn't. At least not in the sense that a derived class can be used in place of its parent. For example, let's say that you have a human class, then an adult class, and then a child class. This may appear hierarchical, but in the context of inheritance, it's not. An adult is a type of human, but a child is not a type of adult, meaning that a child class could not be used in place of an adult, since children cannot do everything that an adult can do, such as going to work, paying bills, or fixing the toilet. This inappropriate hierarchy can be exposed by checking for an is-a relationship, where the child is not a type of adult, but is a type of human. A lot of the time, this will be all that you need to do. But the relationship between your scripts may not always be as clear, in which case the is-a check may not be enough. One way of demonstrating this is with the circle-ellipse problem, sometimes referred to as the square-rectangle problem. In this example, the circle is a type of ellipse, meaning that it is hierarchically correct that the circle inherits from the ellipse. But an ellipse can be uneven in shape, meaning that its width or its height can be different from one another. A circle can't do this, but because it inherits from ellipse, it needs to be able to. This is where the Liskov Substitution principle comes in. A circle is a type of ellipse, but because a circle cannot be used in place of an ellipse, it violates the substitution principle, exposing an inappropriate hierarchy. One possible solution is to reverse the relationship, which makes more sense since the ellipse is basically a circle that can do more, in this case by being extended in width. However, there may still be functionality that a circle provides, such as calculating its radius, that an ellipse couldn't. The Liskov substitution principle is useful as a general test to see if the hierarchical relationship between two classes is appropriate. If it's not possible for a derived class to be used in place of the class it inherits from, meaning that it can't do at least everything that its parent class can, then the relationship is inappropriate. Typically, this may mean that you will need to change the structure of your inheritance, in this case by having circle and ellipse inherit from a shape class instead, or use a different approach entirely. The interface segregation principle states that classes should not implement functions that they don't use. That's pretty much it. The idea here is that in order to make a class universally accessible, you might be tempted to use an interface that contains more functionality than any one object needs. The downside of this is that objects will then implement functionality that they don't actually use, which can be confusing, since when they're accessed, they will appear to offer functions that will more than likely be empty. For example, you might create an enemy interface to deal with the different functions that may apply when interacting with a type of enemy, such as damaging it or stunning it. This would work in that it allows you to create multiple types of enemy that each respond to common enemy functions. But it's possible that not all enemies can be stunned, or you might want to use the same interface that allows you to damage an enemy, but to damage an inanimate object instead. In which case it's generally good practice to use multiple smaller interfaces, such as iDamageable and iStunnable, in place of a larger general purpose interface, allowing you to use the functionality you want while leaving out the logic you don't. In Unity, the benefits of interface segregation are similar to the benefits of single responsibility, and typically you're more likely to run into this issue with components than you are with interfaces, depending on how you're building your game. However, it's still typically a good idea to limit the functionality in your interfaces, especially since they are easy to combine together again. For example, if you still wanted to combine the damageable and stunnable interfaces, you could do that by either implementing both interfaces into a class that uses them, or by creating a combined interface that itself implements both the damageable and stunnable interfaces into one. A possible exception to the interface segregation principle is when you're intentionally using interfaces to create fixed compatibility between classes that are meant to be used interchangeably. An example of this would be state machines, where by design, each state may or may not use a particular function, meaning that it may be empty. While this could be a problem if you find yourself creating very specific functions that are meant for just one state but not the others, offering the same set of functions between different state classes is kind of the entire point of an interface-based state machine. Meaning that while it technically appears to break the segregation principle, so long as each function is relevant to all state classes, it's not necessarily a problem, even when a state doesn't need to use it. The dependency inversion principle is generally quite simple but can be easily misunderstood, which can be a problem, as overusing this principle without fully understanding the point of it can cause you to over-engineer your code. Generally, the point of dependency inversion is to prevent a high-level script from depending on a low-level system. But what does that actually mean? Let's say, for example, you have a class that uses an instance of another class, whether that's a monobehavior or typically a plain class that exists inside of the high-level system. For example, I once worked on a game where I wrote a dynamic music system, where the music player created an instance of a music sequencer when it was running and then passed data to it. The player needed the sequencer in order to work, but the systems were different enough that they deserved to be in separate classes. In this case, the high-level class controls the low-level system, meaning that it directly communicates with the publicly available functions and variables of that system, which works, until you want to change part of it, at which point you'll need to change the low-level system and the controlling class, since it communicates with it directly. This is where a high-level class becomes dependent on a low-level one. The solution is to create an abstraction between the two classes. The music player sends information to a kind of sequencer, but so long as it's able to accept the format of data it's providing, it doesn't care exactly what it is. While the sequencer receives data in the same format, but doesn't need to know where it came from. This creates flexibility through generalization, by allowing the controlling system to use a different low-level system of the same type, and vice versa. This can be useful for swapping out different parts of the system without having to rewrite anything, and for testing, where a test script can now be connected to either part of the system to see if it works as expected. But this principle isn't just about abstraction, since if it was, it would overlap quite heavily with the open-closed principle, which already encourages abstraction to make classes more easily extendable. So when does the inversion part happen, and why is it important? The reason it's called dependency inversion is because under normal circumstances, even though the higher level system controls the lower one, it's the lower level system that sets the rules. If the signature of its functions or its data changes, the higher level system must change as well in order to meet the new requirements, otherwise it won't be able to use it. In which case the higher level system is dependent on the lower level class, violating the dependency inversion principle. The dependency is inverted when the connection is abstracted. This happens because the higher level system owns the abstraction, typically an interface, meaning that it sets the rules of interaction that a lower level system must follow in order to be used by the controlling class. Put simply, the script that is in control now also sets the rules. This loosens the coupling between the two scripts, making either part that little bit easier to change. However, it can be easy to overuse or misinterpret this principle, in which case it's important to identify when you should consider using it. As a general rule of thumb, look out for any scenario in which you create a close relationship between a high and low level class, particularly if it feels like you're writing one script in two places, as this may be a good indicator that one class is dependent on the other. In which case, ask yourself if it makes sense, in this example, for the higher level class to also control the rules of that interaction. If it does, then it might be worth creating an abstraction between the two classes. In the purest sense of the principle, this typically means using an interface, but if you're applying it as a general guidance in Unity, it could also mean using events or messages to broadcast data in a passive way. This achieves the same outcome, where the two scripts are not directly connected, and the controlling script decides what data lower level classes will need to be able to accept. With all of the solid principles, while they can be useful, it is extremely important that you use them as guidelines only. If you try to rigidly enforce all of your code to all 5 of the solid principles, then it's possible that you will never finish your project, since you're likely to spend most of your time over-engineering your code, ultimately making it harder, not easier, to work with. Instead, use the solid principles as a guide to double-check the structure of your project, or to help you to decide between multiple options when you're not sure which is best. And if doing things in a different way would be easier for you, or makes more sense based on how you're building your project, then so long as you're aware of the solid principles and the intention behind them, you can be confident when choosing to go against them.
This video is an excerpt from How to Code in Unity, my no-nonsense course that teaches the C# scripting skills you'll actually use when making a game. For more information, see the link in the video description. Now I want to hear from you. How are you using the solid principles in your game? Do you strictly follow them to keep your project scalable, or do you dip in and out? Or do you ignore solid completely and try to keep your project simple and just hope that it'll work out okay in the end? Let me know in the comments, like this video if you found it useful, and get subscribed for more from me. I'll see you next time.